gas laws, we do this so that the math is easier, but gases don't actually behave this way. And so our calculations are kind of close enough calculations. So some assumptions that we make, or what we think an ideal gas would behave like, is that the particles have no individual volume. So each individual little gas particle doesn't have any volume. Well, we know that's not true. It's a particle, right? It takes up space. So an example would be like a tank filled with helium, like those pink helium tanks that you can buy at Party City or Party Depot or Target or something like that to fill about 30 balloons for a birthday party. So that tank is filled with helium molecules, right? Like these little molecules. In ideal gas law, we assume that those molecules have no volume, but we know they do. It's just they're so teeny tiny that it's no point in even like really thinking about it, but they do have volume. All right, there's no attractive forces between particles. So that means in that little pink helium tank, two helium molecules, they're not interested in each other. They're just bouncing around every which way, and they're not attracted to each other. Now, if we put a sodium ion and a chlorine ion together, right, they're like little magnets because that sodium wants to give that chlorine some electrons, right? But helium, they're just bouncing around. They're not interested in each other at all. So the thought is that when molecules are in gas form, they're not interested in one another. And that our other assumption in ideal gas is that real gases behave this way only at high temperatures and low pressures. So high temperature means that a molecule has a whole bunch of kinetic energy. So it's really excited and it's moving a whole lot. The higher the temperature, the more energy all of those gas molecules have. Also at low pressure. So that means if we have low pressure, that means we're not putting a lot of pressure on those molecules, right? We're giving them a lot of space to move around, and we're not confined. If we put gas molecules under pressure, we're forcing them to be closer to each other. So not only are we restricting their movement, we are making them have greater collisions on the side of the container that they're in. They're going to be colliding with each other more, which changes those attractive forces, right? So putting things under pressure makes things behave differently. We know that from putting people under pressure, right? All right. Okay. So the ideal gas law describes gas behavior under static conditions. That means things aren't changing. It means they're constant. So here is our ideal gas law equation. We call it PIV or PV nRT or PV equals nRT. And let's take a look at what we see here. So P, we know that, all right, so there we go. So P equals pressure. V equals volume. We've learned these guys before. And T equals temp. Well, and notice that we only have one of each of these, so that's because we're not having a change. We're not going from one pressure to another pressure. We have one pressure. So we're saying what is happening to this gas at this one pressure. But we see we have two other new variables. We have N, which is going to tell us the number of moles. So this tells us the amount, right? That's a U, not a no, right there. So think of if you have a balloon and you blow up the balloon with carbon dioxide gas and you hold it, there's a certain amount in there, right? But if you let go of the balloon and it goes flying around the room, that carbon dioxide gas that you put into the balloon is leaving, and there are less gas molecules inside that balloon. So N would be changing. If we take that balloon and we tie it and we hold those CO2 molecules in there, N is constant. The number of moles of carbon dioxide gas in there are not going to change. And then R is a universal gas constant. Let's take a look. There are 3 different numbers for R. Why are there 3 different numbers for R? What do you see that's different in these units? If you said pressure, you are correct. Let's take a look here. So here we have atmospheres, we have kilopascals, and we have millimeters of mercury. Remember, we talked about that we can measure pressure in different units depending on who we're talking to, whether it's a biologist, a chemist, a physicist, an engineer, a mechanic, and there's even more R constants. So for example, we can measure pressure in pounds per square inch, ppsi, like in a tire. That would have a different R because that unit of measurement for pressure is different. How do we know which R to choose? We base it on what unit of pressure we are measuring in. So if our pressure is in millimeters of mercury, then we're going to use 62.4 for our R because of millimeters of mercury right there. If we're measuring our pressure in atmospheres, then we're going to use an R that is 0.0821 because that has the unit of atmospheres for pressure. And you don't have to memorize these, right? You can always look it up if you are doing something with ideal gas law, not something that you need to memorize at all. All right, let's look at a couple of examples here. So here, this is example 1. How many moles of oxygen are there in a 2-liter bottle at 19 degrees Celsius and 747 millimeters of mercury? Okay, so we make our little list here. We're figuring out N right there. That's what it's asking for, how many moles. So we're going to calculate for N. Our volume is 2 liters right there. That's our volume. This is N. Our temperature is 19 degrees Celsius right there. We have our temperature, but remember, we've got to add 273 to get it to Kelvin. And then here we have our pressure. Okay, so that tells us our pressure, and we know which R to use because millimeters of mercury. So we want to have millimeters of mercury in our R, so we use 62.4. And we're going to rearrange the formula to solve for N. So we want N by itself, so we divide sides by R and T. So R and T are going to cancel out, so N equals PV divided by RT. We fill in our numbers, and we end up with moles. And another way you know you did this right is your units should cancel. Millimeters of mercury divided by millimeters of mercury, liters divided by, where are you, liters? Liters, right there, there's liters. K divided by K, this should actually be up here. Sorry, this is multiply. That's multiply by 2.92. You know what, let's cross it out so that it's clear and put it up higher. Multiply by 292 Kelvin. Excellent. And then so we end up, the only unit left is moles right there. So we find out that in this situation we have 0.082 moles. All right, we've got one more example here. Let's take a look. What is the pressure in kilopascals exerted by 1.8 grams of hydrogen gas in a 4.3 liter balloon at 27 degrees Celsius? So we see here our question is, what is pressure? So that is our question, and they're telling us we need to be in kilopascals. That's important so that we pick an R value with kilopascals. Here is exerted by 1 grams. So that's our mass. We'll get back to that in just a second. Here's our volume, and Celsius, there's our temperature. So they gave us mass instead of moles. We know how to convert to moles, right? So we're going to take 1.8 grams and we want to convert to moles. So we've got to put the molar mass of hydrogen gas, which is 2 grams of H2 per 1 mole. That's that conversion we've been doing for a really long time. 0.8 divided by 2, I have there 0.89, but we can just put 9 moles if we want. So there we go. So there's our N. We have our volume in liters. Our temperature, remember you got to add 273 to get to Kelvin. Right? So there's the Kelvin. And R, we just look up and we make sure that we have the right units for that pressure right there. All right, so we're solving for pressure. So we're going to divide both sides by V to cancel V out on this side and have pressure by itself. So that's our new formula. And we're going to fill everything in. And we see here that we have that 8.31 for R because of kilopascals. Here's N, here's T, and here's V. So we multiply across the top, divide from the bottom, and there's our answer. All right, good job, guys. And that is how you use ideal gas law.